Today's lesson is over section 2.7, the derivative as a function. So the definition of a derivative is if f of x is a function, the derivative of f, which is denoted as f prime of x, should be given as the following: the limit as h approaches 0 for f of x plus h minus f of x divided by h. Okay, so here, if I'm given a function, let's say square root of x, and I want to find the derivative of f of x, so f prime of x, I'm going to plug this in. So remember, it's asking you to take x plus h and plug it into the function. So since it's square root of x, it'll be square root of x plus h. And plug those two in. And then the function at the end is by itself divided by h all the time. Now, to be able to kind of do this right now, if I plugged in 0, I would get undefined in the denominator. I wouldn't be able to do anything, so I can't do that. So I need to rationalize the numerator, like we practiced a little bit before. And so that allows me to cancel out some terms at the top, get rid of the square root on the top. Some of the x's get canceled out, and then the h's actually get canceled out as well. So I'm left with 1 over square root of x plus h plus the square root of x. So now I can plug in the 0. That allows me to get square root of x plus square root of x, which is actually 2 square root of x. So my derivative for this function is 1 over 2 square root of x. Now I would like to look at these two functions in comparison to one another. And so if I graph them over the same domain, you notice that the slope of the original function, if we were to kind of describe that, that kind of does look like 1/2-ish. So at that point, and now I know my picture is not fully great, and it might be greater than that, but that value is 3/4, and it kind of does look like 3/4. If I went a little bit further out, that one looks a little bit more like 1/2, and the value I graphed below is actually 1/2. And so you might start to see a pattern that when I plug in a value for the derivative, that actually talks about the slope of the original function that we had gotten it from. And so that's kind of what the derivative is describing. It's talking about the slope of your function, of the previous function, so that you can kind of describe the function as different things. So that's kind of what we're using the derivative for. Now we want to be able to find the derivative, and so that's what the definition of derivative allows us to do. Now this is a kind of a long process for some problems. Sometimes it's pretty short and sweet. Sometimes it can be a little obnoxious. So there are different ways of kind of going about this that you kind of want to keep in mind, but a lot of this stuff is just really algebra that we're using to help do these things. So like for letter A here, just like we did before, I'm plugging in x plus h into the original function for that first piece, and then the second piece is just the original function. Now, once I do that and distribute all the stuff through and kind of simplify, I need to make common denominators with both of the fractions. And so then I need to kind of go through and multiply all the stuff out. It looks like I'm taking a binomial times a trinomial and doing that both top and bottom. Notice that I don't do it with the bottom because eventually I will be able to simplify that a little bit differently once I'm able to plug in what h is. So I'm going to leave that denominator on the top by itself. Now notice, once I do this, I'm able to cancel out a whole lot of stuff, and I'm left with negative 3h in the numerator, or the very top numerator. But I still have a complex fraction here. So remember that h is the same thing as h over 1, and so complex fraction, I want to keep it, change it, flip it. So I'm going to multiply by the reciprocal of 1 over h. That allows me to cancel out those h's, and then I'm able to now plug in 0 into the fraction that I have. And notice that for the thing in the denominator, it's actually the same. I have 2 plus x times 2 plus x, which there's 2 of them, and I can write them as a paired binomial together, so 2 plus x squared in the denominator. And that's my derivative for this one. Okay, same thing with letter B. I have x cubed minus x. I'm going to plug in x plus h into both. That's the first part, and then I'm just going to have the original part for the second one. So that's what the 2 big parentheses are for. Now, same thing, I have to multiply all that stuff out. But once I do, I should be able to cancel some things out, which will be very nice. So notice I get the x cubes away, the x's. I'm not able to get as much as I did the last one, but that's fine. Here, they all have an h in common, and so then I'm able to reduce everything away from h. And then from there, now that I got rid of the denominator of h, I can plug in 0 for h because I no longer have the problem of getting an undefined value. So 2 of them will get multiplied away because of 0, and that leaves me with 3x squared minus 1 as my derivative for f of x. Okay. Now, there are other notations for your derivatives. You have y prime, dy over dx. The dy over dx means that you're taking the derivative of y with respect to the derivative of x. You can do that with df, so the derivative of the function with respect to x, or d over dx, that's the same thing. There's other notations like d or capital D of f of x. They all mean the same thing. They're all talking about the derivatives. Now, a function of f is differentiable at a if f prime of a does exist. Now, what that means is that if I can find a value, or if I can actually define what that value is there for the derivative, then it is differentiable. I can find that derivative there if it's already defined for me. Now, there are a few questions to ask here. Does continuity imply it's differentiable? And that is actually no. Just because something's continuous doesn't mean it's always differentiable at that position. Does differentiability imply continuity? Actually, yes. If I can find the derivative, then that means it has to be continuous by the definition of differentiability. So those two things are not always the same for these problems. So based on that, here are a few examples that will help us kind of determine when things could be in this weird spot. So letter 1 is actually continuous, but because of that cusp or corner, it's actually not differentiable at that spot because the slopes are heading to two different things. For number 2, it's obviously discontinuous there, so they do not have the same limit heading to different spots at the value of a. And then also for number 3, here you have a vertical tangent line because of how it is. It is still a function and is still continuous, but because of how the line kind of curves down like that, at a particular point of a, it will become a vertical asymptote. So our slope is undefined, so it's not actually differentiable there. So definition, if f is differentiable at a, then f is continuous at a. So here's an example where I have the function of f of x is the absolute value of x. Is it just differentiable there? So looking at those two sides, you're going from on the left going down to 0. From the right, you're going down to 0. So your limit is true. It's the same. But if you actually take the derivative on the right side, your equation is x, which the slope is 1. On the left side, as you're approaching 0, the slope is -1. And so those values are not approaching the same thing. So it's not differentiable at that spot. So then we have to split up the differentiability to two spots, from -infinity to 0 and 0 to infinity. Okay. Now, we also can find the second derivative of our function just like we did the first derivative. So for letter A, we already found the first derivative from a previous example for x cubed minus x. So we already know it's 3x squared minus 1, but I do the exact same process to find the derivative of the second by plugging in that x plus h into the function to begin with, and then subtracting it from the original function, and then distributing out all the terms, seeing what cancels. Looks like we get some 1s and some 3x squareds to cancel out. And then I'm able to reduce everything by a value of h. And that leaves me with 6x plus 3h. And then I can plug in 0 in for h so that I can find the derivative, which is 6x. So the second derivative would be 6x for this problem. Letter B, if you're not given the previous one, you'll have to find it. So like for letter B, I have to plug it into two places, just like I did for the x cubed minus x in the previous example. So I plug in x plus h into the first function, or the function itself, and then minus the original function. Then I multiply all my stuff out. Several things should cancel. Get some 6's, 5x, x squareds go away. I'm left with 2xh plus h squared minus 5h, and then I can reduce everything by an h. Leaves me with 2x plus h minus 5. Get rid of that middle h because I plug in 0. So my first derivative is 2x minus 5. And now I can do the same thing for the first function, or the first derivative, to find the second derivative. So I plug in that x plus h and reduce or multiply all my stuff out. Here, 5's and 2x's cancel out. I'm left with 2h. And then 2h divided by h leaves me with 2. Now here you have nothing to plug into h, so it's really just 2 for my second derivative, and that is totally fine. And then that would be my answer. Now here, when we're doing second derivative, we can also find the third. One thing we'll talk about a lot is position functions. And so S of t is a position function, so position of where something is on the graph, like for a particle or something. The first derivative is representing the velocity of that function, so the speed in which it's going. The second derivative represents the acceleration of that function, so like how fast it changes from one speed to the next. And then the last one is called the jerk function. That's the third derivative. And so that is like how fast it's changing its acceleration. And so one kind of just leads into the other, but dictates or kind of tells a story about what your function is doing as it goes along. Okay? Have fun.